Hello, my name is Marion Sudvarg. I'm a PhD student at Washington University in St. Louis, and on behalf of the ADAPT collaboration, I'm going to be presenting fast gamma-ray burst source localization pipelines. We're developing the Advanced Particle-astrophysics Telescope, which is going to look something like this. The telescope is going to be an orbiting platform that will orbit at the L2 Lagrange point, which is on the opposite side of the Earth from the Sun, and it's sufficiently far away from the Earth that the telescope should have a nearly full sky field of view for detecting gamma-ray bursts. Now, the goals of APT are to detect and localize GRBs in real time using onboard computational hardware. Because this detection and localization is in real time, this will allow APT to promptly communicate its observations with other instruments, including telescopes on Earth, which can then immediately point at the GRB source that's been localized by APT and perform observations in other spectral bands. In prior work, we developed a localization software pipeline and analyzed performance on an ARM Cortex-A53 processor. In this work, we've accelerated 2 stages of the pipeline on a GPU, and we estimate the running time on a 10-watt NVIDIA Jetson NX Xavier system. So this diagram shows a cutaway view of the APT detector hardware. So when a gamma-ray photon enters the instrument, it Compton-scatters multiple times. And FPGA-based hit detection sporadically writes collections of scattering interactions into memory for each gamma-ray photon that enters. Now, the problem is that for an individual photon, the time resolution of the instrument is not sufficiently fine to describe the order of interactions. So in prior work, we've described an algorithm to reconstruct this ordering, essentially to guess which is the first scattering event, which is the second scattering event, and so on. Now, this is important because the first 2 implied scatterings allow us to describe the initial source direction of the photon. So from the first 2 implied scatterings, we have a vector c, which is from the second scattering event to the first scattering event. And this vector c describes the center of a cone. Now, additionally, from the Compton law, we can determine the scattering angle of the first scattering of this photon. And that scattering angle phi describes the opening angle of the cone. So now, from the first 2 implied scatterings, we have a cone that describes the set of possible initial source directions for this gamma-ray burst. Now, additionally, we have a value sigma, which is the propagated uncertainty of measurement error. And sigma smears this cone out in space, essentially creating an annulus with some uncertainty upon which that initial source direction must lie. Now, during a typical GRB, several thousand photons must be reconstructed, and the resulting source direction of the GRB can be estimated based on multilateration of the produced annuli. So to perform this multilateration, first, we try to guess an initial approximate source direction based on a coarse-grained approximation technique. The way we do this is from n annuli that have been reconstructed, we select 20 at random, and we assign each annulus I from those 20 to a CUDA block. Now, for each block, which has an annulus, we select 720 candidate source directions evenly spaced on the circle described by the annulus. So here we show the circle described by a single annulus, and we pick 720 source directions, all evenly spaced around that circle, so spaced half a degree apart. Now we distribute those candidates across GPU threads, and for each of those candidates, we calculate its joint log likelihood to be the true source direction with respect to all n reconstructed annuli. So now on each block, we have these 720 candidate source directions. We now have a joint log likelihood telling us how likely it is that that is a true source direction. And so we select the maximum likelihood candidate, the candidate with the highest likelihood from each annulus. So now from those 20 blocks, we have 20 estimates for the source direction, and we average over those 20 estimates, weighting each one according to its likelihood to produce an initial approximate source direction S sub 0. Next, we take this initial estimate S sub 0 and we use further linear least squares refinement iteratively to get a better estimate of the true source direction. So within each iteration, we test whether each annulus I from our n reconstructed annuli lies within 3 sigma of the estimate S. So in our diagram here, we have multiple annuli, and we have an approximate source direction S sub I. Now for each annulus, we see if it lies within 3 sigma of S sub I. So you can see that these green annuli do lie within 3 sigma of S sub I, whereas these red annuli do not. So now for those green annuli here that do lie within 3 sigma of our estimated source direction, we generate linear constraints C sub I dot S equals cosine of phi sub I. We additionally require S to be a direction vector, so this creates a unit norm constraint which is quadratic in the coordinates of S. This allows us to reduce the problem to a quadratic eigenvalue problem. Forming the matrix for this problem is O of n squared in the number of annuli, so it's quadratic in the number of annuli that are actually being used. The matrix dimension is proportional to the 3 coordinates of S. So now what we can do is we can parallelize steps 2, 3, 4, and 5 in purpose-specific CUDA kernels. Next, we solve on the CPU with the eigen library to get a refined estimate for S. Now we perform this refinement iteratively 20 times, feeding this new refined estimate back into the refinement stage again, and after 20 iterations, we have a final solution S, which we say is our estimated GRB source direction. So now, how well do these algorithms do? Well, we tested this by simulating GRB interactions with our detector using JAUNT4, which is a particle physics simulator produced by the folks at CERN. Now here in our chart, fluence describes the energy density of the detector GRB, and it's worth noting that input size is proportional to fluence. So for higher fluence events, we have more photons, essentially more input data to reconstruct and localize, which means that we typically get better results with higher fluences. In fact, we achieve consistent subdegree localization for high fluence events, and the subdegree localization is important because the apertures of the telescopes that we're communicating with from APT tend to be around 1 degree of aperture opening. And so that means that subdegree localization is sufficient to point these telescopes close enough to the true source direction of the GRB that they can still see it. Now, in our prior work, we developed these algorithms to target an ARM Cortex A53 CPU. And so we measured execution times on that CPU. Again, recall that fluence is proportional to the input data size. So for each fluence tested, we measured execution time over 200 trials for each fluence. And as you can see, this initial source approximation stage and the iterative refinement stages are what dominate the execution time. And this is why we decided to target these 2 stages for acceleration on our GPU platform. So we measured our GPU accelerated pipelines execution times on an NVIDIA GeForce RTX 2080, and then we scaled these execution times to estimate performance on an NVIDIA Jetson NX Xavier board so that we could compare these performance measurements to our original CPU implementation. As you can see, our CPU execution times are marked here in blue, and our GPU execution times are marked here in orange. For the initial source approximation stage, we achieve an estimated speedup of 3 to 3.5 times, which is very promising, especially considering that the initial source approximation stage had dominated our runtimes on the CPU version. Now, acceleration of the iterative refinement stage does slow the increase of execution time with input size. However, because execution switches from the CPU to the GPU for each iteration, we incur significant overhead for the GPU implementation. Now, in future work, we will attempt to reduce this overhead, and we're optimistic that our accelerated iterative refinement stage will also present significant speedup. So that's all, and thank you for watching.